bit late now, but we'll see how far we get. My name is Alfred Körlein. I come from Munich in Germany originally. Now I live in Nuremberg, but I worked with the Environmental Institute in Nuremberg and Munich. So I will introduce a KIC study, which is an abbreviation for childhood cancers near nuclear power plants. The study done in 2007, or published in 2007, that found highly increased cancer rates and especially leukemia rates near German nuclear power plants, all combined. There's someone speaking in the back and I don't know. Yeah, speaking. This study was commissioned, I'll go a bit shortly over the first part, was commissioned in 2002 by Federal Office of Radiation Protection in Germany, our highest institution for radio. Okay, thank
you. One small general for Lithuanian translation is number one. Just one translation works so far, technically.
Yeah. And it was conducted by the German Cancer Registry, Childhood Cancer Registry. We don't have a general cancer registry, but for children we have a cancer registry. The results were presented in 2007, and yeah. So the study design was a case control study that was new. We had studies done before in Germany and other countries, like Great Britain, and some other countries like Switzerland. But this study was new so far as this study approach is more sophisticated, needs more time and money, and this was probably the reason why these results were so significant. All cancers and leukemias were studied. All German nuclear power plants were included. Children below age 5 only were considered, and the data range was from 1980 to 2003. Now, this was a study region. There were regions around nuclear power plants, altogether 16 regions, based on districts or counties. The main result was this significant increase of cancers and for leukemia. Then we had found a relative risk of 1.6 for cancers, which means a 60% increase in the 5 kilometer zone compared to the rest of the study area. And a nearly 2.2-fold increase for all leukemias. Then there was the excess. To date, the KIC study is the most powerful study worldwide of childhood cancers near nuclear power plants. The results are as seen on this graph. We have here the distance on the horizontal axis, and on the vertical axis there's a relative risk. We find out that in the 5 kilometer zone, that's the first plot, the risk is significantly increased compared to the risk in all other distance zones. And you see that even in the 5 to 10 kilometers distance zone, the risk is not increased. These results are, as the KIC authors said, consistent with most international studies, because before they usually didn't find increased or significantly increased risks. So, and then they said the results were unexpected given the level of radiation exposure. The causes are unknown, they said, but radiation can be ruled out. Radiation is far too low to produce such effects. Or they speculate about unexplained confounding, whatever that is, and so other possible influences means confounding, or even a chance result. Although this result was highly significant, they still allow for a possible chance result. Now there were other studies initiated after the KIC study was published. One study was in Switzerland, was the last one, in 2009. It was a cohort study, it was a different design, but covered a pretty long time, also 24 years, or 25 years. And then in Great Britain, there was also a study done also on children below age 5, all children below age 5, and leukemia. And always the comparison between the 5 kilometer zone and the rest of the study area. Then in France, a very small study that only covered a very short time period, for only 9 years. And then an additional study was done in Germany on the basis of the KIC data, but using a geographical study design, which means that they used only districts and the distance from a cancer case from the NPP, the nuclear power plant, was just defined by district midpoint. So it's not as precise distance as in the KIC study, where every case and every control was located precisely by a house. They know the address of the household. Now, when you compare now the results of these studies, Switzerland, Great Britain, France, and Germany, and you do a pooled analysis of all data together, you find in the individual studies you hardly find an increased, significantly increased risk, but the risk estimates, called relative risk, that is this column here, is comparable. Like in Switzerland, they have 1.46, then in Great Britain 1.41, in Germany it's 1.45, and only in France, but there's only 5 cases in the 5 kilometer zone, there's no significant or no increase at all. But altogether, including France, we find about 40% increase, which is clearly significant. So we can't say that other studies contradict the KIC study, contrary is true. Other studies add to the significance of the KIC findings. If you plot now the data in individual studies and try to do a regression analysis, so to find out that there's a distance trend, you can apply a 1/r distance trend, and you see that the data points fit well together, and the trend is significant also. Now they say, okay, the estimate, we find the risk is doubled, more than doubled, but the doubling dose for leukemia is estimated at some millisieverts after in utero exposure, the first trimester of pregnancy. Then the official dose estimate for 1-year-old children are some microsieverts, so a factor of 1,000 smaller than the doubling dose of leukemia. That's why they say it's implausible that the cause of this increase is radiation, ionizing radiation from nuclear power plants. That is just a plot for you. The red columns are the effective dose for children, and you see they vary from one nuclear power plant to another, but they are all in the range of some microsieverts. So we know now that what could be a possibility to explain this phenomenon in terms of radiation exposure. There's critics that say that official dose calculations use simplified propagation models, then the action of internal radiation are underestimated by the existing ICRP model. Then all values that are used to calculate doses are just given as fixed values without a confidence range. If you allow for a variation in doses and then you can easily have a factor of 10 more just by the variation in dose estimates that are not considered by these models. So the official risk estimate might be low by a factor of 10 or 100, but we need to explain a factor of 1,000. So, how to close the gap? The usual assumption that risk is proportional to average dose is only correct if the dose-response relationship is linear, meaning doubling dose, double risk, for instance. But do we know the shape of the dose-response curve for prenatal leukemia induction? The dose rates from MPPs show large variations in time and space, while dose rate from natural background radiation is rather constant at a given location. So that's a plot where you see the plume of a nuclear power plant, the fallout plume of a nuclear power plant, and you see so-called ESA lines where you have if you see the inner ellipse and compare the value that is attached to that to the outer ellipse, you find a factor of 10,000 difference in ground deposit radius. So there is a huge difference, local difference in dose or just in ground deposition of radiation. So this is local variations. Now, I'll come to time later on incontinuities of emissions. Okay, here I found a slide in a presentation on teratogenic risk. This is by the University of Leipzig in a course of therapy. And you see that they call the induction of cancer and leukemia, they relate to teratogenic risks. And then if you look at another slide that I found on the internet where they show the dose-response curves for stochastic effect as compared to teratogenic effects. So usually cancer induction is thought to be a stochastic effect. But if you allow for the possibility that that is also a teratogenic effect, and when it is in utero, then things might be quite different. Because if you now increase dose, you find a factor of 2 of dose. Let's say if you are at the threshold here, you have no effect, but a factor of 2 here, you have a huge effect. So now, this is just to make it a bit clear. If you would have, let's say, a power of dose, that means dose response, which is rising with dose steeply, and you would have an annual dose from MPPs, which is 10% of natural dose, and you calculate now the 3 weeks initial peaks, you would get a 112% increase of risk just mathematically, just because the dose response curve is not linear. So 10% increase of dose would make a 112% increase of risk. As I say, just a mathematical model. And you can vary now the parameters and an assumption, and it's according to this assumption you can get between a 27% increase and a 640% increase, just depending on the parameters. The blue parameters define more or less the steepness of the curve, and so you can see that you can have effects only because the dose response relationship is not linear. I will show you now the discontinuity of the global gas emissions, because these data are available from our local governments, like on a provincial, like Bavarian government provided these data. This was the last refueling in September and October 2011, and you see the normal. This is a linear plot, and here you don't see any concentrations. That is the concentration of noble gases in the stack. So it's all comparable to 0, but then it jumps up in the 38th calendar week in September this year from 3 kilobecquerel per square per cubic meter to 1,470 kilobecquerel per cubic meter, so a factor of 500. If you plot that now on a logarithmic scale, you see that that is a 2-month period, September and October. You see before the fuel change or refueling, there was about the 3 kilobecquerel, and you see here that it took a long time to get back to the level of more or less 3 kilobecquerel after the refueling period. Now this is only one calendar week, the 38th calendar week, just to see the facts a bit clearer. How small the timing is. This is actually these 2 days, day 22 of November, 22nd of September, 23rd of November. The bulk of radiation came out in only 2 days. This is now the same in a logarithmic plot, but here you see below the gray points are the data for the week before refueling started. So you see that it's a pretty constant, just random variation around this 3 kilobecquerel. Now I apply as a dose response relationship, not some power to the dose function, but for statistical reasons I apply a log normal distribution function. I can't go into the details now, but just applying this model here to the data of the concentration, I can show, and if you go from concentration to releases of radiation, the releases are proportional, let's say, to concentrations, with, if you know the airstream, 130,000 cubic meters per half hour. Multiply that by the concentration, you get the releases per half hour, and then you sum up all half-hour releases, and you get in the data that I have, only for the 2 months, you get the sum of all releases. And then you assume that in the rest of the year you have the releases in the same level, more or less, than observed before the refueling at about 3 kilobecquerel concentration. And then you can estimate a total annual release that is about 17 terabecquerel per year. And only in this the first day when they opened up the reactor, the 23rd of September, Of this, 18% of the total releases were emitted in only one day. The second day, together with the first day, 32, nearly one-third of all releases came out in only 2 days. And in 1 week, about half, nearly half of all releases came out in 1 week. So it's extremely sporadic. So now we have to go from releases to doses, and to that we have to assume the total dose. I said, okay, let's assume that we have an error in the dose estimate of about a factor of 10 from the official dose estimates. And we say, assuming a dose of, say, 50 microsievert from NPPs, and relate that to the releases over the year, then we can calculate doses from the releases. And we add these doses to the background doses. Then we get the doses here per half hour. And we see now, this is the 38th calendar week, so we see the relative dose divided by the relative dose divided by the background dose sort of reaches more than a factor of 10 in 1 half hour in the middle, and one here about it's nearly a factor of 10 increase compared to the average dose over the year. So, and then from dose to relative risk, we can now sum up all these. Now we apply our log normal distribution function and can recalculate doses into risk by using this relationship between dose and risk. Then we form an annual average of the relative risks over all months of the year, or all half hours of the year. And then we get, as a result, more than twofold increase. If you assume a 5% increase of dose from background level, we can calculate with this model a 118% increase of risk based on the emission data. I mean, that's all a mathematical model with a lot of assumptions as to the form of a dose-response relationship and so on. But what I want to show is that with certain assumptions, you can show that what the statement of our Radiation Protection Commission, that these effects cannot be explained by radiation. So radiation has to be ruled out as a possible cause of these increased cancers, cannot be upheld. I show here the relative risk again, after transforming risk into the doses into risk that we get in certain days or half hours, you get up to a relative risk of 350 compared with the background. So, yeah, summary and conclusion, that's the last one. Leukemia in children under 5 years is more than doubled. The official dose from nuclear power disease is some microsievert per year. Doubling dose for leukemia after utero exposure is some millisievert, 1,000 times greater. Aerial radioactive discharges from NPPs are highly episodic, mainly during fueling and inspection. If dose response is curvilinear meaning strongly upward trend, effect increases disproportionately with dose. Conclusion, the present result challenges the assertion of official radiation protection agencies that radioactive releases must be ruled out as a possible cause of increased leukemias in NPPs. Thank you very much for your attention.